So temporal difference methods are basically a small variant of the kind of methods that we've seen until now for approximating the optimal policy of optimal policies of stochastic games, with the difference being that they are specifically designed for unknown environments. So it's a kind of extension of the methods. So methods which work for a known environment can be deployed in an unknown environment, but temporal difference methods are a variant which will do better. For example, we'll avoid getting stuck if the environment suddenly changes in an unexpected way. So I'm going to introduce this by kind of expanding on, instead of trying to say what it is at first, I'm going to expand on the idea slowly. So the most basic method is, suppose we're in some state and we take some action and we watch what the environment does, and we see that the environment transitions to some new state and we receive some payoff. What we're going to do, the most basic thing, is that we can update our value for the old state to the payoff that we got plus discounted value for the new state. And this also, by the way, works if these states are observations rather than true states. So notice that here we're not taking an expectation. We are actually letting, because the way that the environment responds is going to be potentially random. So we're just going to watch what it does. We're essentially kind of sampling its distribution. So this is very closely related to Monte Carlo value iteration, but it's subtly conceptually different, because in Monte Carlo, we know the distribution and we kind of duplicate, we simulate the distribution ourselves. We do the randomness ourselves in the algorithm. Whereas this, we simply let the environment do its thing, which is random. So we let the environment do the randomness for us. So the end result is basically the same, but conceptually it's a bit different. And as I said in the previous video, this can also be combined with simultaneously learning a policy. Now, at this point, if we're learning about the environment through interacting with it, we have the usual thing with Monte Carlo and reinforcement learning methods, which is that we have to balance exploration and exploitation. These are two different goals which are potentially in conflict with each other. So exploration means playing actions with the specific goal of improving our knowledge of our environment, whereas exploitation means playing actions with the goal of obtaining high payoffs. And these two things are different goals. And we have to balance these. So this is, again, part of the art of reinforcement learning, is how do you balance these two goals. So reinforcement learning methods are often what's called off-policy methods. So you're learning a policy, which is your estimate of the best policy, the one that's going to lead to the highest payoffs. So off-policy methods are reinforcement learning methods that don't always play what it currently believes is the best move. In other words, it sometimes does something else in order to satisfy the exploration goal. So this is quite similar to the perfect, as in subgame perfect and Markov perfect equilibrium. In other words, this is going to work in kind of arbitrary states off equilibrium, where equilibrium means on the path of playing the optimal policy. So the simplest off-policy method is to just sometimes play a random move. These can get quite advanced. So there are reinforcement learning methods that actually simultaneously learn two different policies, one for the exploitation goal, which is your kind of target policy that you're actually trying to learn, and the other one is called behavior policy or behavioral policy, which is a policy that's used for the exploration goal. And you update these in two different ways, reflecting your different goals for them. Okay. Now, if we have an unknown environment, it's important to distinguish between what's called stationary and non-stationary environments. So if we have something that we know, or say strongly believe or model as a Markov chain, but a potentially unknown Markov chain, this is called a stationary environment. So stationary environment roughly means that this thing is a well-defined Markov chain with a well-defined transition, probabilistic stochastic transition function. We just don't know what it is. We only have to learn it. A non-stationary environment essentially means all bets are off. A non-stationary environment, we could assume some things about it, but in the most extreme, we can assume absolutely nothing. This environment could be absolutely anything. It doesn't have to behave. It doesn't have to satisfy the Markov property. It doesn't even have to have well-defined probability distributions. So reinforcement learning for non-stationary environments is where kind of the really cutting edge stuff happens. This is where you really go far beyond the setting of classical control theory. So it's worth saying that if you're in a multi-agent learning setting, if you have multiple reinforcement learning agents interacting with an environment, even if the environment is stationary, remember I said that the agents form part of each other's environment. So if you're one of these agents, your extended environment consists of the true environment, which is stationary, but also the other agents, and the other agents are using learning algorithms, which typically don't satisfy the Markov property. So this means that suddenly you're in a non-stationary environment. So yes, as I said, so the real power of reinforcement learning methods is that they're effective heuristically in non-stationary environments. In general, if you assume very little about your environment, you can, theoretically speaking, say very little. So you can't kind of guarantee convergence or anything like this. But heuristically, these methods do extremely well in practice often. Okay, let's get to the details, kind of the real equations that are used. So for learning in a non-stationary environment, how can we do it? Well, the basic update rule. So suppose the same setting as before. We're in some state, we do some action, and we watch what the environment does. We see that it transitions to a new state or new observation S1, and it gives us the payoff U0. The basic update that we can do is whatever was our estimate of the old state, we can increment it by this thing, where we have U0 plus the discounted value of the new state minus the value of the old state, but all of this is scaled according to some other parameter. And this is a sort of learning rate or step size. Now, you can see that when alpha is 1, this term is going to cancel out with this term, and we're going to get back exactly the formula that we used before for value iteration. So we can see this as a extension of value iteration. And at the other extreme, when alpha equals 0, we stop learning. So when alpha is somewhere between, when alpha is some other value in general, it doesn't necessarily have to be between 0 and 1, I think. This thing is going to do some kind of approximate value iteration, but which is robust to the environment doing unexpected things like spontaneously changing to something else. So if our environment is non-stationary, this learning rate is the thing that avoids us getting stuck if it changes, for example. Another thing to note is this alpha doesn't necessarily need to be constant over time. So one thing you can do is, for example, is decrease it over time, make it converge to 0. As long as it never reaches 0, you will, at least theoretically speaking, never get stuck. Another thing you might want to do is dynamically vary it according to kind of how surprising the environment's behavior is, so that if the environment does something that you really didn't expect, you might suddenly want to kind of switch back on fast learning, for example. Okay, let's talk a bit more about multi-agent learning, multi-agent reinforcement learning. So in a stochastic game, or more generally, if we have a multi-agent setting with an unknown environment, each agent can estimate their own individual copy of the value function. So to say the value function that is giving the value of just that agent's payoffs, and they could also learn their own individual policy. So as I said, these value and policy iteration, kind of the learning methods that we're using, don't satisfy the Markov property. As I say, what they do depends on their previous values. So this causes each other's environments to become non-stationary. So we can see this where, so if we have multiple agents, multiple reinforcement learning agents interacting with an environment, at each stage, then each agent is going to choose an action, and then the environment is going to transition to a new state and give each agent back some payoff, potentially a different one. And the payoffs that each agent get are going to depend on, in general, on the actions that all of the agents took, as well as the current state. So this is like a stochastic game, except that the game is no longer common knowledge. So there are some variants of this. So, for example, the actions that each agent just took in the previous round might be revealed as part of the observation state in the next round, or they might not be. And if you think about real life games, both examples of this exist. Say you're playing chess or Go, you always know what your opponent just did. Whereas if you're playing StarCraft, the complete state your opponent's move may not be immediately known, although some of them might be known to you if they're right next to you. So notably, we are now at this point outside of the realm where you can really say much theoretically. There is no general guarantees that this thing is going to converge to a Markov perfect equilibrium or any other game theoretic equilibrium. So at this point, we kind of fall off theory and into a mixture of cutting edge research and wild informed speculation. So in my personal opinion, this is not a kind of generally accepted thing yet. I'm optimistically saying yet. In my opinion, the thing that multi-agent learning converges to, which is a combination of policies, aka a strategy profile, deserves to be considered a kind of game theoretic in the new generation sense solution concept in its own right. So I am interested in studying kind of the game theoretic study of whatever it is that multi-agent learning converges to. So this is typically not an equilibrium in a game theoretic sense, but because of kind of theoretical similarities, theoretical connections between game theory and reinforcement learning, it is kind of an equilibrium-like object. It's kind of the limit of a process of simultaneous maximization.